In electrical engineering, the power factor of an AC electrical power system is defined as the ratio of the real power flowing to the load to the apparent power in the circuit, and is a dimensionless number in the closed interval of -1 to 1. A power factor of less than 1 means that the voltage and current waveforms are not in phase, reducing the instantaneous product of the two waveforms. Real power is the capacity of the circuit for performing work in a particular time. Apparent power is the product of the current and voltage of the circuit, due to energy stored in the load and returned to the source. A negative power factor occurs when the device generates power, which then flows back towards the source, which is normally considered the generator. In an electric power system, a load with a low power factor draws more current than a load with a high power factor for the same amount of useful power transferred. The higher currents increase the energy lost in the distribution system, and require larger wires and other equipment. Because of the costs of larger equipment and wasted energy, electrical utilities will usually charge a higher cost to industrial or commercial customers where there is a low power factor. Linear loads with low power factor can be corrected with a passive network of capacitors or inductors. Non-linear loads, such as rectifiers, distort the current drawn from the system. In such cases, active or passive power factor correction may be used to counteract the distortion and raise the power factor. The devices for correction of the power factor may be at a central substation, spread out over a distribution system, or built into power-consuming equipment. Linear circuits. In a purely resistive AC circuit, voltage and current waveforms are in step, changing polarity at the same instant in each cycle. All the power entering the load is consumed. Where reactive loads are present, such as with capacitors or inductors, energy storage in the loads results in a phase difference between the current and voltage waveforms. During each cycle of the AC voltage, extra energy, in addition to any energy consumed in the load, is temporarily stored in the load in electric or magnetic fields, and then returned to the power grid a fraction of the period later. Because HVAC distribution systems are essentially quasi-linear circuit systems subject to continuous daily variation, there is a continuous ebb and flow of non-productive power. Non-productive power increases the current in the line, potentially to the point of failure. Thus, a circuit with a low power factor will use higher currents to transfer a given quantity of real power than a circuit with a high power factor. A linear load does not change the shape of the waveform of the current, but may change the relative timing between voltage and current. Electrical circuits containing dominantly resistive loads have a power factor of almost 1.0, but circuits containing inductive or capacitive loads can have a power factor well below 1. Definition and calculation. AC power flow has three components: real power or active power, expressed in watts; apparent power, usually expressed in volt-amperes; reactive power, usually expressed in reactive volt-amperes. The VA and VAR are non-SI units mathematically identical to the watt, but are used in engineering practice instead of the watt in order to state what quantity is being expressed. The SI explicitly disallows using units for this purpose or as the only source of information about a physical quantity is used. The power factor is defined as the ratio of real power to apparent power. As power is transferred along a transmission line, it does not consist purely of real power that can do work once transferred to the load, but rather consists of a combination of real and reactive power, called apparent power. The power factor describes the amount of real power transmitted along a transmission line relative to the total apparent power flowing in the line. The power triangle. We can relate the various components of AC power by using the power triangle. Real power extends horizontally in the I direction as it represents a purely real component of AC power. Reactive power extends in the direction of J as it represents a purely imaginary component of AC power. Apparent power represents a combination of both real and reactive power, and therefore can be calculated by using the vector sum of these two components. We can conclude that the mathematical relationship between these components is increasing the power factor. As the power factor increases, the ratio of real power to apparent power increases and approaches unity, while the angle theta decreases and the reactive power decreases, decreasing the power factor. As the power factor decreases, the ratio of real power to apparent power also decreases, as the angle theta increases and reactive power increases, lagging and leading power factors. In addition, there is also a difference between a lagging and leading power factor. A lagging power factor signifies that the load is inductive, as the load will consume reactive power, and therefore the reactive component Q is positive as reactive power travels through the circuit and is consumed by the inductive load. A leading power factor signifies that the load is capacitive, as the load supplies reactive power, and therefore the reactive component Q is negative as reactive power is being supplied to the circuit. If theta is the phase angle between the current and voltage, then the power factor is equal to the cosine of the angle. Since the units are consistent, the power factor is by definition a dimensionless number between -1 and 1. When power factor is equal to 0, the energy flow is entirely reactive and stored energy in the load returns to the source on each cycle. When the power factor is 1, all the energy supplied by the source is consumed by the load. Power factors are usually stated as leading or lagging to show the sign of the phase angle. Capacitive loads are leading, and inductive loads are lagging. If a purely resistive load is connected to a power supply, current and voltage will change polarity in step. The power factor will be unity, and the electrical energy flows in a single direction across the network in each cycle. Inductive loads such as transformers and motors consume reactive power with current waveform lagging the voltage. Capacitive loads such as capacitor banks or buried cable generate reactive power with current phase leading the voltage. Both types of loads will absorb energy during part of the AC cycle, which is stored in the device's magnetic or electric field, only to return this energy back to the source during the rest of the cycle. For example, to get 1 kilowatt of real power, if the power factor is unity, 1 kVA of apparent power needs to be transferred. At low values of power factor, more apparent power needs to be transferred to get the same real power. To get 1 kilowatt of real power at 0.2 power factor, 5 kVA of apparent power needs to be transferred. This apparent power must be produced and transmitted to the load in the conventional fashion, and is subject to the usual distributed losses in the production and transmission processes. Electrical loads consuming alternating current power consume both real power and reactive power. The vector sum of real and reactive power is the apparent power. A negative power factor can result from returning power to the source, such as in the case of a building fitted with solar panels when the power is not being fully utilized within the building and the surplus is fed back into the supply. Power factor correction of linear loads. A high power factor is generally desirable in a transmission system to reduce transmission losses and improve voltage regulation at the load. It is often desirable to adjust the power factor of a system to near 1.0. When reactive elements supply or absorb reactive power near the load, the apparent power is reduced. Individual electrical customers who are charged by their utility for low power factor may install correction equipment to reduce those costs. Power factor correction brings the power factor of an AC power circuit closer to 1 by supplying reactive power of opposite sign, adding capacitors or inductors that act to cancel the inductive or capacitive effects of the load, respectively. For example, the inductive effect of motor loads may be offset by locally connected capacitors. If a load had a capacitive value, inductors are connected to correct the power factor. In the electricity industry, inductors are said to consume reactive power and capacitors are said to supply it, even though the energy is just moving back and forth on each AC cycle. The reactive elements can create voltage fluctuations and harmonic noise when switched on or off. In the worst case, reactive elements can interact with the system and with each other to create resonant conditions, resulting in system instability and severe overvoltage fluctuations. As such, reactive elements cannot simply be applied without engineering analysis. An automatic power factor correction unit consists of a number of capacitors that are switched by means of contactors. These contactors are controlled by a regulator that measures power factor in an electrical network, depending on the load and power factor of the network. The power factor controller will switch the necessary blocks of capacitors in steps to make sure the power factor stays above a selected value. Instead of using a set of switched capacitors, an unloaded synchronous motor can supply reactive power. The reactive power drawn by the synchronous motor is a function of its field excitation. This is referred to as a synchronous condenser. It is started and connected to the electrical network. It operates at a leading power factor and puts VARs onto the network as required to support a system's voltage or to maintain the system power factor at a specified level. The condenser's installation and operation are identical to large electric motors. Its principal advantage is the ease with which the amount of correction can be adjusted. It behaves like an electrically variable capacitor. Unlike capacitors, the amount of reactive power supplied is proportional to voltage, not the square of voltage. This improves voltage stability on large networks. Synchronous condensers are often used in connection with high-voltage direct current transmission projects or in large industrial plants such as steel mills. For power factor correction of high-voltage power systems or large, fluctuating industrial loads, power electronic devices such as the static VAR compensator or STATCOM are increasingly used. These systems are able to compensate sudden changes of power factor much more rapidly than contactor-switched capacitor banks, and being solid-state require less maintenance than synchronous condensers.